Good morning students. Last class we have discussed De Morgan's theorems and derivation of Boolean expression. In that we have seen a small part or minimum part of a min term. What is a min term? It is nothing but product of all literals. Literals are nothing but variables x, y, z. For example, a, b, c. These are the variables. With a literal can be with a bar or without a bar. That is nothing but with a complement or without a complement. So within a logic system, such a thing we call it as the min term. In min term is also called as the sum of the product. And last class we have seen steps involved in solving the min term. First one, write down the SOP, that is nothing but sum of the product as it is. Next, if any term is missing, any variable is missing in a term, multiply that term with its complement. Then remove, that is drop out all the duplicate terms. So these are the steps we have seen in the last class. Today's class will see other procedure for expansion of code. What is the other procedure? Means first write down the terms. First one is write down the terms. Next one, put x term. Put x in each term if variable is missing. Third one, use all combination of x in each term. Then fourth one, drop out the duplicate term. So what it tells you is, first you write down the term, whatever the given expression, put x in each term if a variable is missing. Next, use all combination of x's in each term. You are going to vary the x's only, that is the missing out the letters. Then after finding out that, after writing all possible combination of x's, then you are going to drop out the duplicate terms. So now we will using that procedure we will solve this particular expression AB plus C. You write down the AB plus C as it is expression. See where the missing term here. In AB there is C is missing. In C there is AB is missing. So put x, that is AB x plus xx C. So I am placing x where the term is missing. Now AB x. Okay, I am taking each term. Use the possible combination of x's. X is nothing but here C. So here ABC, ABC bar. In one term you can write it, only C can be changed with C or C bar. That is the one possible combination in your ABX. Now in your XX C, so here that is nothing but XX here stands for AB. So one possible combination is A bar, B bar, C. Okay, A bar, B, C. Next A, B bar, C. Next as it is without complement A, B, C. So you got in first term you got 2 expression. Second term you got 1, 2, 3, 4 expression. You add this, you add the terms. You add the first term. First term you have 2 possible combination. In second term you have 4 possible combination. Add that one. A, B, C plus A, B, C bar plus A bar, B bar, C plus A bar, B, C. Next next A, B bar, C plus A, B, C. So this is the procedure 3 as well. Next, after writing the possible combination, fourth one is drop out the duplicate. Which not duplicate here it is? A, B, C. Any other possible combination? 1 A, B, C. So I am writing as it is A, B, C. Any other possible? Here, no, same it's not there. So see the possible combination. The other expression, write it as it is. A, B, C bar plus A bar, B bar, C plus A bar, B, C plus A, B bar, C. So when you taking this expression, that is A, B plus C, using the other procedure of expansion, you got the expression A, B, C plus A, B, C bar plus A bar, B bar, C plus A bar, B, C plus A, B bar, C. So you want to check this particular thing, whether this got the expression is it is a correct SOP, you are going to cross check it using the you are going to minimize the steps using the rules. That will see how to minimize the steps using the rules. So you got the expression after adding the each term and dropping out the duplicate things. Now we will arrange it is according to your bar, your complement A bar, B bar, C plus next A bar, B, C plus A, B bar, C plus A, B, C bar and this A, B, C as it is plus A, B, C. So you got the expression till here. Now you see which are the common terms in this. Here it is A bar, B bar. Now here C, A bar, sorry, here A bar, C is common, A bar, C is common. Here B bar plus B as it is. Now it doesn't have any common term between this. I am writing A, B bar, C as it is. Plus when you compare these two, A, B is common, A, B plus into C bar plus C as it is. Now you got A bar C. A bar C as it is. According to your complementary law, x plus x bar is equals to 1. In place of x here it is b. B plus b bar is equals to 1. That is b bar plus b. 1. Plus A B bar C as it is. Plus again the same rule. X plus x bar is equals to 1 according to your complementary law. Again it is 1. So you got the expression A bar C plus A B bar C plus A B. Now A bar C as it is plus here we are going to see which one is the common term. Here it is common term is A. Okay. Here A is the common term. B bar C plus B. Okay. A is the common term. This is according to your distributive third law, that is x plus x bar y is equals to x plus y. Here what it is? X holds the b value, x bar y holds the that is nothing. This is your x bar y. So I am going to write it as A bar C as it is A into B plus C. What's my B? X here it is B. C is nothing but according to your absorption law or distributive third law, you are going to use this particular rule. Now you got the expression that is nothing but A bar C plus you are just multiply AB plus AC. So you have to get the solution AB plus C. So here you write this AB as it is. In this two things A bar C plus AC, AB as it is. Okay, which one is the common here? C, A bar plus A. That is nothing but AB plus A bar plus A is nothing but according to your complementary rule, x bar plus x is equals to 1. So that is nothing but C into 1. That is nothing but AB plus C. So you have proved the whatever expression got through your procedure of expansion of the code using SOP. After getting the expression, you want to cross check the expression, just minimize according to your rules or De Morgan's theorems, then you can come back to the original expression. So till here we have solved. Next is the max terms. Before going to max term, let us see how shorthand notation can be used in your min term. So it will be a 1 mark question, shorthand representation of a particular term. Suppose first thing what are the rules followed? First copy the things. After copying the term you are going to write the equivalent binary values. After writing the binary values, you represent in the decimal equivalent. Here always your min term is represented in small m. And here it is as used with the, you are going to see in your canonical min term and max term. There I will explain what is the difference between a summation and pipe. But time being you understand, min term is represented with an expression small m. So for example, I am given the copy the term. Let the term be A, B bar, C bar. So here I have already explained in min term, bar represents 0, that is complement. Without complement, uncomplement or usual represented by 1. So here it is A is nothing but without complement. So it is 1. This is nothing but B bar is nothing but 0. C bar is nothing but 0. So this is a binary equivalent of the term. First copy the term. Now what's what's my term? I have copied and written the binary equivalent. Now you get it to a decimal equivalent. What's my decimal equivalent? No? You know, people have studied in your first year, your decimal equivalent in your third chapter, the data representation. That is your decimal is nothing but, this is in the binary form, everything is multiplied with 2's. So 0, 1, 2. 1 into 2 to the power of 2 plus 0 into 2 to the power of 1 plus 0 into 2 to the power of 0. So 1, 2 square is nothing but 4. Here 0 into 2 to the power of 1 is 1, only once 2. Next 0 into 2 to the power of 1 is 1. Next 1 into 4 is 4 plus 0 into 2 is 0 plus 0 into 1 is 0. So what's my decimal equivalent is 4. So the term given for this min-term representation is nothing but M4. The min-term representation, what did you got the decimal equivalent here? It is 4. So this is the shorthand representation of your min-term. Okay. The next topic is nothing but max term. When there is a min-term, usually there will be a max term. This max term is nothing but sum of the min-term is a product of sum. Here max term is min-term is sum of product, SOP. Then min-term is POS, product of sum. So here what it says means it is nothing but sum of all literals. It is nothing but sum of all literals with or without bar within the logic system. We call it as the max term. See, once again I am telling, max term is nothing but sum of all literals. The literals can be with or without complement. Such a thing within the system, within the logic circuit, we call it as the max term. So each sum, it is sum term. Here we have considered the sum term. In sum term, it should consist of all literal. That each literal should be added. That each sum should be multiplied with the other sum term. That is the rule used in your max term. Here in max term, it is represented by your bar is represented. Suppose bar is represented by 1, non-bar or without bar it is being represented by, without bar it is being represented 0. What it tells means if a variable or literal, if it is x means it is represented as 0. With x bar means here it is 1. Just opposite of your min-term. There we have studied in min-term bar means complement, bar means 0. 1 means without bar. But here, if your variable has a without bar means here we are considering 0. If it is a variable or literal has a bar means we are considering it as 1. So such an expression which has a sum of all literals with or without bar, we call it as the max term. In max term it is represented by capital M. It is represented by capital M. So next topic is canonical expression. This canonical expression can be represented either min-term or max term. In other way I can say canonical expression is composed entirely either as min-term or max term. Such an expression we call it as the canonical expression. Once again I am telling, canonical expression is nothing but it composes of two things, that is a min-term or max term. In more way you can say, in other way, more systematic way you can say means canonical expression composed entirely either of min-term or max term. Such an expression we call it as the canonical expression. So I have told you the canonical expression can be of min-term or max term. In a min-term, when you consider, we already studied min-term is also called, that expression is also called as the sum of products or standard sum of products. So values derived in here, sum of products comes in under two things. One, it is various possible input values, the possible way of inputting the values. Next, the output values, the derived or desired output values for each combination. Whatever input value is given, you are going to get the desired output values. So these are the two possible ways you are going to get the values in your SOP, that is sum of product. Sum of product can get the values from two things. One, it is the possible input values. For each output value, it gets the values from the input combination. So now we will see the one problem, then you can understand SOP. So you consider an example in SOP. You have two input and Z operation or AND operation or NOT operation, simply with the help of two input values, the two input values nothing but 2 square. So four possible input as it is 0, 1, 2, 3 multiples of 2. For this 2 input you got Z as the output function. So for this you have to write the product term. So product term I have already told you. In this side you can mention it is for 0 it is x bar, y it is y bar. For 0 it is x bar, for y it is what it is, y as it is. For 1 it is x, for 0 it is y bar. For both it is x, y. Okay. So you represent in the form of product term. So x bar, y bar. Next x bar, y. Next x, y bar. Next x, y. So you have got the product term, or it is also called as the min term. For this particular x and y, there is an output z. You just leave the z. For this x and y literals, you write the product term. So now our expression can be represented in SOP means which output got 1. Your z is your output, no? Which expression got the 1? Only consider that particular expression. So here 1, 1, 1. Your min term takes the expression if the output is 1. Okay, I am explaining. Your min term takes the expression only if an output you get the high values, that is nothing but 1. So here the expression is x bar, y bar. I am not considering 0 output. Next x, y bar. Next x, y. So this is my canonical SOP. This form of expression we call as the canonical min term expression or canonical sum of product expression. See here, they given another example program. X, y, z are the input variables. F is a function or output. How they obtain the F function using some condition. What is the condition here it is used with? If the input value is odd input value, that is odd input value 1 means the function will be 1. The output will be 1. See here consider 0, 0, 1. So the input value is only odd. Odd is nothing but 1, 3, 5 odd numbers. 5, 7. These are the odd numbers. So here it is 1. So output using some condition. This function will be given using some criteria. In your exam point of view, the output will be given. So otherwise they will trace you to giving like this condition. You get the function output if the input has the odd number of ones. In such a case you have to trace this particular. Here even this has, because only one input 1. Here two input are there. So the 2 ones. So it is not odd. So it is given 0. Here one input is there. So 1. Here 2 input 0. Here also 2 input 0. Here 3 input 1, 2, 3. So odd number 3. So based on that condition you are getting the function f, your final result or output. See once again I am telling this x, y, z till here you are writing the input according to your binary values of zeros and ones, that is 2 to the power of 3 is nothing but 8. That is 1, 1, 2, 4. 0, 1, 2, 3, 4, 5, 6, 7. I have already explained how to represent 0, everything 0. For 1 it is 1, for 2 it is 1, for 3 2 plus 1, 2 plus 1, 4 in place of 4 1, other 0, 5 4 plus 1 is 5, 4 plus 1 is 5, 6 4 plus 2 is 1, 4 plus 2 is 1, 4 plus 2 is 6, so 1 1 0, 7 4 plus 2 plus 1 is 7, 4 plus 2 plus 1 is 7. So till here you are writing. If in exam point of view they have given the final result, output result, no problem. If they give some condition, you have to concentrate what the condition they have given. You have to write the output function based on the odd numbers of input. Based on the odd numbers of input. In such a case, they have given the condition here which all has the odd input. Odd numbers are nothing but 1, 3, 5, 7. Like that, which is not multiples by itself, which is divisible, that we call as the odd number. A number which is divisible by itself by 1 we call as the odd number. So according to that they are given the function. So your product term, that is nothing but your literals you are going to perform. Here for every, I have already told, if it is 0 means it is bar. If it is 1 means without bar. For this product term I am taking, okay, what it tells means this is a second example. This is y bar, z bar. Next, here you are going to represent x bar, y bar, z. Here x bar, y, z bar. Here x bar, y, z. Here x, y bar, z bar. Here x, y bar, z. Here x, y, z bar. Here x, y, z. Once again I am telling, if it is 0, you put a complement. If it is 1, place same as usual variables or same literals you can represent. So 3 zeros, 3 bars. 2 0 1. So 0 1 z. 0 bar, y as it is, z as it is. So x, both the condition bar bar. 1 1. So 1 1 bar. So 1 1 z. So this is your product term or min term. I have already told, to get the product term or min term, you have written based on your values of zeros and ones. Now you have to perform a canonical expression. How you are going to perform a canonical expression? Based on the output which has 1. So what's my output which has the expression 1? That is nothing but x bar, y bar, z plus x bar, y, z plus these two over. Now have this one plus x, y bar, z bar. Next this one x, y, z. So this is my canonical expression of the given function x, y, z. X, y, z as a variable, the function f. So this is we called as the canonical function of SOP. Okay. So the next method of your SOP is your algebraic method. What it tells in your algebraic method is nothing but first thing it tells, first rule or rule 1, what it tells means simplify the given expression using any De Morgan's theorem or using any other rules. Any kind of laws can be used to solve this particular De Morgan's particular expression SOP. How you are going to help out in your algebraic method means first one, bring as it is x bar y plus x z bar. In your De Morgan's theorem, I have solved, complement the entire function, change the or to and to or. So here x bar y plus x bar z. So I am complemented, first rule I have used, complemented the entire thing. Next, you are changing, that is x double bar. Here into is there, I am using plus. Okay, into here x double bar, okay, plus z double bar. So I am complementing the entire thing. I am changing your into, that is and sign to your plus sign to your and sign to your plus sign. So here it is. So the twice if you complement according to your involution law, you get the same result, x plus y bar. So into x plus z. So you got the result. That is nothing but x, you take it as out. That is nothing but x. That is nothing but 1 plus y bar into x plus z. You get the relation, that is 1 into, that instead of plus into you have, that is nothing but 1 plus x is equals to 1. That is 1 plus, that is into it. So after complementing the entire thing, so I am splitted the complementation, that is y bar into, I have changed the sign. So x double bar is nothing but your same variable, that is y bar into x plus z. This is according to your distributive law. What it tells means x into x plus y, that is equals to xy plus xz. Okay, here x is that is what it x is equals here x. Next yz is nothing but plus y bar z. Till here you got the expression. So next we will see how to simplify this given expression. First rule, you are going to use the De Morgan's theorems or any other rules, then simplify the given expression. After getting this first rule over, the second rule what you are going to use means in your SOP, if any literals or any literals that is absent in your product term, you are going to multiply with particular term plus or plus your missing term. So here x is there, y, z. See, you are having three variables. What is the missing term here is y, z. Here missing term is x. In first condition it is missing. yz. In second condition it is missing x. So x as it is, we are going to multiply with y plus y bar. Okay, next z is missing, z plus z bar. Okay, next plus as it is. Next what here it is missing, x. Okay, x plus x bar into y bar z. This is the given expression. Once again I am telling, in a SOP I have already told in the first rule method, in steps involved to solve the method. If in a particular term, in a product term, if any term is missing, you have to multiply with the particular variable and its complement. I am multiplying with a variable plus its complement. So here what it tells us, here yz is missing. So I am placing y plus y complement. Z is missing, z plus z complement. Here only x is missing. So I am writing x plus x bar into y bar z. So next just multiply this xy plus xy bar. That is nothing but z plus z bar. Here as it is you write x plus x bar into y bar z. Next now we multiply this with particular thing, x y z plus, okay, x y bar z plus this term, okay, this term x y z bar plus this term x y bar z bar. Next this term x y bar z plus x bar y bar z. After you got the expression, see whether any duplicate. Rule 2 I have used, rule 3 drop out the duplicate terms. A term is repeated more than times. See x, y, z present anywhere? No. X, y, z. Now x, y bar z. X, y bar z. It is present here. So once I write it plus x, y bar z. Next, see anything which has x, y, z bar. No. So I write it x, y, z bar. Next, x bar, x, y bar, z bar. No. X, y bar, z bar as it is. Next, x bar, y bar, z. So this is the canonical expression or min-term expression using an algebraic method. First thing, you have the given expression using De Morgan's law or any other law, solve it. When you solve, you get the expression. Now you find out any literals is missing in each term. If these literals are missing, multiply with that particular missing literals plus its complement. Then solve the application. You will get the expression. That expression we called as the canonical expression of sum of product. The next topic is the shorthand notation of SOP. So what are the rules used in a shorthand notation? First rule is binary equivalent. Convert the given find out the binary equivalent of decimal subscript. They given the decimal subscript. You have to find the binary. You have to find the binary equivalent. What it tells means find binary equivalent of decimal subscript. The decimal number 0 to 9. For that you are going to find the binary equivalent, that is zeros and ones. For given decimal you are going to find the binary equivalent. After finding out the rule 1, then you are going to write in rule 2. You are going to write for 1, if a binary equivalent is 1 means write the variable as it is. If a binary equivalent is zeros means write its complement. These are the two rules used in a shorthand notation of SOP. So, for example, you take an example. If arise a 1 mark question, so x, y, z are the variables. Find out the binary equivalent of this particular given decimal subscript. We find the binary equivalent. Write the SOP form or canonical expression form means. Then what you are going to do means f. Okay. Here m0. This is I have already taught. If you want to find which is min term or max term, if it is small m is there means you are going to consider it as min term. That is nothing but SOP. M0 means that is nothing but 0 plus 1 plus 2 plus 5. That is nothing but binary forms. So in binary forms it is 3 input. What will be the variable? 0, 0, 0. For ABC like that x, y, z. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1 0 0 1 0 1 1 1 0 1 1 1. This is your binary. When you solve a min term or max term, you have this based on the input. You have this binary representation. For 0, what it is? This is m0. What it is? 0 0 0. Write it as it is. m1 0 0 1. They have given m2. What's my m2 here? 0 1 0. Next, they have given m5. So 1 0 1. This is my binary equivalent. Find the binary equivalent of the decimal subscript. This is my decimal subscript. Okay, subscript. This is m1. Okay. Now you write it in the form of expression. This is nothing but x y z. So x y z. For here it is. If it is 0 means everything bar. X bar, y bar, z bar. So x bar, y bar, z as it is. Next x bar, y as it is, z bar plus x as it is, y bar, z. So this is my Boolean or this is my canonical expression of SOP using the shorthand notation of SOP, that is find the decimal equivalent of given decimal equivalent. You are going to find the binary equivalent, then write 0 when it zeros means complemented, 1 means as it is the literals, then you form the expression. Such an expression whatever you have formed, that we call it as the canonical SOP. Using a shorthand method, you are going to perform a canonical SOP or canonical min term expression. So next one is canonical product of sum, that is we call it as the POS, or it is also called as the max term. So this max term is nothing but sum of all literals or a variable with or without complement. Such a thing we call it as the max term. So here in this max term, so it is represented, I have already explained, represented by capital M. Okay. In max term, you are going to represent the expression with help of pi. Okay. In your min term, it is represented with help of summation. It is represented in a canonical expression. It is represented. Here I am placing small m, that represents your min term. Here I am representing a capital M means with a pi, and a capital M means it is nothing but my max term. Students don't get confused. If it is given a summation and a small m means you consider it is as min term or SOP. If they given a pi and if it is represented in expression or a binary equivalent or decimal equivalent, if they given a pi and it is given as f of, if they given f of like this, xyz is equals to, if they given pi and capital means it is max term, or it is also called as the POS. That is nothing but sum of all literals with or without complement in a logic circuit, we call it as the max term. In your max term, 0 means it is nothing but your 0 means as it is the variable, 1 means here it is complemented. We will see a truth table of a max term. Okay, here in a product of sum, there is a truth table given. A function of xyz is my variable function. For that I have to find out the sum term or max term. Here they have given the 3 inputs, so 2 to the power of 3 is nothing but 8 possible ways. 0, 1, 2, 3, 4, 5, 6, 7. You go either for 2's multiple 1, 2, 4. For 0 everything 0, and for 1 it is 1. The remaining place is 0. For 2 is 1. The remaining place is 0. For 3 is 2 plus 1. 2 plus 1 0. For 4 it is the 4 in place of 4, place it 1, the remaining place is 0. In 5, 4 plus 1, 4 plus 1, 0. 6, 4 plus 2, 1, 1, 0. 7, 4 plus 2 plus 1, 4 plus 2 plus 1. For this particular input values, xyz function of xyz, they were given the output as f. They are based on some evaluation, they are given the output condition, that is 1, 0, 1, 0, 1, 0, 1, 1. For this, we have to perform a sum term or max term. So, I have already told, if it is 0 means as it is, 1 means complement in your max term. So, here 0 means, so here it is, this is x, y, z. I have already written here x, y, z. So, x bar plus, here it is sum term. So, x bar, each literal should be sum. Okay, y bar plus z bar. This is one thing. Next, x bar plus y bar. Okay, 0 means as it is, not bar. Sorry. 0 means as it is. 0 means as it is. So x plus y. Z in place of z, 1 it is there. So z bar. Once again I am telling 0 means as it is a variable. 1 means complement. 0 also I am writing x plus y plus z. So 0, x as it is, y as it is, 1 it is there. For that I am writing z bar. Next, here it is 0 as it is. Here it is 1. So y bar. So 0, z as it is. Here, okay, 0. So x. 1, 1. So y bar plus z bar. Here 1 it is there. So x bar plus y as it is, z as it is. Here, okay, x bar plus y as it is, z bar. Okay, next here, okay, x bar plus y bar plus z. Next here, 3 cases, everything is 1. So x bar plus y bar plus z bar. Got it? Once again I am telling, if it is 0 means, see the binary value 0 means, write the variable as it is, literal as it is. If it is 1 means, change it to a complement. So here it is 1, so z bar. Here in place of 1, here it is 1, so y bar. Y and z are 1, so y bar, z bar. Here in place of x it is 1, x bar. X and z is 1, so x bar, z bar. Next 6, x and y are 1, x bar, y bar. Here in the 7, that is the input value, last one, 1, 1, 1. So x bar plus y bar plus z bar. So in your, how you are going to get the output expression for your product of sums? If the final output is 0, which has the value 0, that will be going to consider the output expression. In your min term, you take only 1, which has the output expression 1. But in max term, just quite opposite of a min term, the final output which has the value 0, you are going to consider for that as the output. Take the expression x plus y plus z bar. Okay, sum of into product. What you are going to write it as this one, x plus y bar plus z. Okay, z bar. Yeah, z bar. Next, these two finish. Next, which has the output here? Here. Next, into x bar plus y plus z bar. See, once again I am telling. See, we are going to take the output expression for this POS or max term, canonical max term means which has the output function or the function which has the output which is 0, that is considered as the output expression of your canonical POS, which are terms as the output expression is 0 here, that is the holds the value of some term x plus z bar. Next, this particular thing which has the output value x plus y bar plus z bar. Next, you have the third expression, that is nothing but x bar plus y plus z bar. This is the canonical expression of your product POS, product of sum, with help of your truth table. Next, we will see algebraic method. So the next topic in your POS or max term is algebraic method. How you are going to simplify the given expression and you are going to get a canonical POS is the algebraic method. In that there are 5 rules. First rule, simplify the given expression. Simplify the given expression using De Morgan's theorems or rule. You can apply any De Morgan's theorems or any other rules in your Boolean algebra. Next, after applying the rules, next you are going to get the second rule. What it is means, convert the product of sum forms. Convert the given expression into product of sum forms. You are going to convert, okay, by applying the algebraic rule. After doing De Morgan's rule, you still more you want to convert into product of sum form using any of the Boolean algebra rule. Either you can use the De Morgan's theorem in the first rule or any other rule. Otherwise, again, if you want to still more convert into POS, use the algebra rules, Boolean algebra rules. After doing it, after converting, getting to a form of POS, after converting into POS term, if see that each term, each sum term, if there is any literals or variable is missing. If you find any literals or variable is missing, Boolean algebra rule. After converting into POS form, you know that still more you cannot be converted. After converting, see whether there is any literals or variable is missing. If you find any literals or variable is missing in each sum term, I am making use of the word sum term. In POS it is called as sum term. If any sum term is missing, add that variables or literals with missing term into missing term bar. Okay, after adding, you are going to, you keep on simplify the given expression using a distributive law, that is nothing but x plus yz is equals to x plus y into x plus z. After adding that missing term, you keep on simplifying the expression using this one rule. That is a rule, that is nothing but a distributive law. That is your first distributive law. That is a second distributive law. Distributive law, you know, x plus yz is equals to xy plus xy into x plus z. After simplifying this particular rule or law, then whatever expression you get, drop out the duplicate terms. You have to drop out the duplicate terms. After dropping out all the duplicate terms, the remaining sum terms is being multiplied. Then you get the expression. Such an expression we call it as the canonical POS. Okay, student, we have seen the algebraic method. What all rules are there? First term, they are given an expression x bar y plus y into z bar plus y. This is the given expression. Using an algebraic method, you have to give an expression into POS or maths term. So take the expression x bar y plus y. Okay, multiply this one z bar plus z bar into y. Okay, so you have omitted a one inner bracket. So using a distributive law, that is your x into x plus y. So x that is nothing but x into x plus y is nothing but xx plus xy. Using that law, I am using this rule. So using a distributive law, x bar y, I am just multiplying z into z bar z plus z bar y. So write this step x bar y plus y. This z bar, idempotence law, variable with its variable using and or you get the same variable. That is using idempotence law. What it tells, a variable combined with itself using a variable, let it be or operator or and operator, the same variable. So z bar plus z bar y. Now we got the expression. Next, x bar y plus, you see the common thing, that is nothing but y z bar. So 1 plus y. So here x bar y plus y z bar. This is nothing but according to the properties of zeros and 1, that is 1 plus x is equals to 1. So here 1 plus, instead of y x it is 1, instead of x it is y. So it is 1. So you get the expression x bar y plus y z bar. So using the first method, using the first rule of your algebraic method, the given expression, you can either use a De Morgan's theorem or any Boolean algebra rules. You are going to solve the solution. So first rule I have applied using a distributive law. Just I have multiplied, that is x into x plus xy, that condition. So distributive law, x into x bar is z into z bar is a z bar plus y is nothing but z bar y. So as it is written, z bar into z bar according to idempotence law, first law, I have solved a variable combined with its a variable using a or and, it is same variable. So same thing, what it here it is complemented. So I have taken the same complement plus z bar y. So in this thing, see which one is common here, z bar. So z bar I made it as out. The one thing is left is 1 plus 1. 1 plus y. So this is according to your properties of zeros and 1. 1 plus x is equals to 1. So 1 plus x, instead of x here it is y. So 1. So x bar y plus y z bar, that is nothing but you got the expression using your first rule under algebraic method. But this is not a proper product of sum. You have to use a second rule. Again simplify using any one of the Boolean algebra. Simplify using any one of the Boolean algebra in order to get into first rule we have got the expression x bar y plus y z bar. So x bar y plus y z bar. Again in the rule 2 it is not a proper product of sum. So we are going to again simplify the given expression using any one of the Boolean algebra. Here we will consider one Boolean algebra, that is nothing but your distributive law. What is this distributive law says means x into what it tells means x plus yz is equals to x plus y into x plus z. That is what according to this is my distributive law. In this what it tells means x plus yz is equals to x plus y into x plus z. So I am considering, okay, this is my x and this is my y and this is my z. So here what's my form, it is x bar y plus y as it is into, okay, this is my x, this term is my x and this is y stands y, z bar is nothing but z. So I am taking x bar y as it is as my x, y here it is y into x bar y plus z here it is z bar. So again further this can be again used a distributive law, that is nothing but here it stands for x and this one stands for yz and here also it stands for x and this one stands for yz. Again apply a distributive law. So here what is my x here it is, this is x y plus x bar into y plus this is y. Okay, this is one term expression, that is I am again using a distributive law. My second rule is if it is not in a proper POS, convert, simplify into using any of the rules of a Boolean algebra. So I am using a distributive law. The given expression is x bar y plus y z bar. So I am using a distributive law. What's my distributive law is nothing but x plus y z. Second rule under B in a distributive law, x plus y z is equals to x plus y into x plus z. Here x holds the variable x bar y as it is z bar. So I converted it into this form. Next again this one to use the distributive law, y stands for x bar y stands for yz. Here z bar stands x bar y stands for yz. So I am taking y as it is. So my y x as it is. What's my y here it is? X bar into x. This is x as it is. What's my y here it is? What's my z here it is? Y. So one thing we have finished. Again this you multiply. What you got here it is z bar. Okay, x. What's my y here it is? X bar into z bar. What's my z here it is? Y. So now y plus x bar. So this is according to idempotent law, a variable combined with itself using a AND or get the same variable y. Okay, next z bar plus x bar. Okay, next z bar plus y. Z bar plus y. Now you according to your commutative law, that is x plus y is equals to y plus x. So you arrange it according to a variable, that is x, y, z. So x bar plus y as it is, x bar. Okay, x bar plus z bar. Next, okay, next y plus z bar. Now this came into a correct POS form, product of sum form. Next we will use third rule, that is using a distributive law. We are going to keep on simplifying this one with which is a missing term. Missing term is absent. Then you are going to add your missing term into missing term complement. Using that one with help of distributive law, you are going to keep on simplifying your given expression using third rule. See here, using first rule and second rule. In a rule 3 got a proper POS. Here you are going to apply the third rule. What the third rule is telling means, you see each term or each sum term, you are going to find any term, that is sum term is nothing but it's a sum of all littles, that is you are going to add all variables. See here in this particular thing z is missing here, here xy is missing, here y is missing, here is x is missing. So you are going to, according to your max term rule, you are going to add your missing term plus into missing term bar. That is nothing but what I am going one term I am taking x bar plus y. This is my first term. What is missing here? Here it is z. So I am writing as x bar plus y plus I am going to add. I am not going to multiply. I am going to add in your POS. Add your missing term into missing term bar. Okay. Now you got the expression, that is x bar plus y plus z into z bar. So this is not proper POS. POS sum of each that is each individual literal should be added, but it is not in the form of product. Again it should be simplified. So you consider this one. So I am taking using a distributive law. Third rule is solve using distributive law. Consider this is my x and this is my yz. So what's my formula? X plus yz is equal to x plus y into x plus z. This is my formula. Here I am taking x as it is, x bar plus y plus z. Next, x bar plus y plus z bar. So furthermore, we cannot simplify the first term. So this is the first term sum product. What it is in more shorter way, you can represent it in a zeros and ones. Bar means 1, as it is means 0 in your max term. Bar means 1, as it is means 0, 1. So this takes the hold of what value, that is remain x, y, z. You always keep a table of 3 input. It's a 3 input variable. So 1 0 0 is nothing but my n4 into 1 0 1 is nothing but my n5. So first term has been solved. Okay, second term is nothing but y. See, y, x is also missing as well as y is missing. So that you are going to add your missing term. Then how you are going to add means here x into x plus bar plus y as it is. Arrange it is accordingly. Next z plus z bar. So you have added a condition, that is a missing term. What is my missing term is this? Here it is x and x bar. I have added, that is I am not multiplying, I am adding x into x bar, y as it is your second term, z into z bar. Now use the distributive law. Now you consider this one is my x and this is my yz. So x bar, okay, plus y plus z into x bar y plus z bar. Okay, see here I am considering this one as my x term, x, and this one is my y, z. So according to the distributive law, x plus y plus x plus z. So x is nothing but x bar plus y, y is nothing but my z. Here x is nothing but x into x bar plus y plus z is nothing but my z bar. Again this is not in a proper POS form. Now you consider this is my x and this is my yz. So arrange it properly. Now what here it is? It's telling means x into y, x into, that is x plus y into x plus z. So x y plus z. What's my here? Y here it is x. This one term. Next, x is nothing but y plus z. What's my z is nothing but x bar. Got it? Next again this one, y plus z bar plus x into y plus z bar plus x bar. So arrange according to a commutative law all x, y, z, because to the function should be taking the binary equivalent. So x plus y plus z into x bar plus y plus z. Next x plus y plus z bar. Next x bar plus z bar plus y. So the second POS form came into an existence. So first we have seen for first term missing literals, for second term. Now for third term is nothing but y is missing here. So take it as x bar plus y into y bar Here, now when you consider this as x bar plus z bar plus y bar. Okay, this is the term they have given. So in this is my x and this is my yz. Use the distributive law. So x bar plus z bar, okay, plus y into x bar plus z bar plus y bar. Okay, so here, listen here. So this is my x term, this is my y term. So I am using a distributive law. X plus yz is equals to x plus y into x plus z. So x bar plus z bar plus y into x bar plus z bar plus y bar. Okay. Now you write the what's the binary equivalent. So bar means 1. Here 1 0. Here 1 1 1. So this holds the value of m6 and this is nothing but m7. So next we will see the fourth term. Next, my fourth term, we have solved first term, second term, third term. My fourth term is y plus z bar. What is y plus z bar? What is missing here is x. So x into x bar plus y plus z bar. So this is my expression after adding the missing term into missing term bar. So here this holds the x and this is my yz. So y plus z bar plus x into y plus z bar plus x bar. See, use a distributive law, you got the expression. Now after getting still more, you cannot go for POS. Rearrange using a commutative law. X plus y plus z bar into x bar plus y plus z bar. So here what it tells means, right here, what is the binary equivalent? That is 1 means 0, 0. Here z bar means 1. Here 1, 0, 1. That is nothing but it takes holds the value of m1 and this one is m5. So we have taken first term we have seen x bar plus y. First term we have solved. Next y. Next for third term. Next for fourth term. Now you are going to what's product everything. That is you are going to add everything and remove all the duplicate things. After removing what expression we are going to get it, we will just write it on that expression. So after solving each term by term, you get totally for first term expression, for second term I have given the expression, third term, fourth term. The total term has been written and the binary equivalent, that is decimal equivalent, this is capital M, that is your max term. For first term M4, just to solve it, that is 100. Keep on writing further. You can get M4, M5, M0, M4, M1, M5, M5, M7, M7, M1, M5. So these are the terms expression and shorthand notation I have given for each thing. Now drop out the duplicate ones. So 0 is there, 1 it is being repeated twice, so I have written 1. 4 it is being repeated only 2 times, I have written 1. 5 it is being repeated 1, 2, 3, 4 times, so written 5 only once. 7 as it is. So for this expression I am writing for m0 what is means, that is for m0 that is x, y, z, no bars. m1 so okay, for I have written according to x, y, z. For m4 x, y bar, z bar. Okay, this is for 1. Okay, for 1 I have written. Okay, for 4 I have written. See, I have written according to the numbers, but it is being rearranged alternatively. So for 0 I have written every numbers. For 1, only 1 has been highlighted. Other thing is as it is. Next for 4, it is bar x, y, z. 5 bar. For 7, everything bar. So till here concludes the that is algebraic method using POS. Next class we have seen shorthand representation of POS. If you have any doubts, put it in your assignment questions. I'll try to solve that particular all the doubts. Thank you.